Hello, students. Welcome back to Unit 2 Basic PLC Programming. In the last session, we went through seven types of basic gates, which are the building blocks of a digital system. We saw their working, the symbol of the gate, then we also went through the truth table and the logic equations used to represent a logic gate. Now, in this session, we'll be looking at what a ladder diagram is, how it works, then conversions. Uh, and we go through the rules for the conversion, how to convert these logic gates into a ladder diagram, then rules for conversions. All these things will be covered in the present session. So in the earlier session also, I told you about a ladder diagram. Let me recap it. A ladder diagram consists of two fundamental parts, vertical lines and horizontal lines. The vertical lines are called as the rails, and horizontal lines are called as rungs. A rail carries the power. The one rail carries 24 volts DC. The second rail carries 0 volts DC. Input contacts, the output coils, they are connected in the rungs. And for the output coil to be energized, there should be a connection between the two rails, and this connection is established by closing or opening the input contacts. Now, how this ladder works is, here you could see there are number of rungs here. The rung 1, 2, 3, and 4. So, out among these four rungs, which one the ladder will take a preference and which one is executed first? In what order it will be executed, these rungs? And that is dealt in working of the ladder diagram. Here you can see I have taken four rungs here, rung 1, 2, 3, and 4. The ladder, it scans the rungs from top to bottom. That is, first it will scan rung 1, later on 2, then 3, and at last it will scan 4. And in the rung there will be many contacts here. So how it will within in a same rung there are many input contacts, so there you should have the preference here. So it scans a given rung from left to right. So whichever the contact is at the leftmost position, that will be scanned first, and then the second contact will be scanned. So the ladder diagram or is it works like this. The PLC uses top to bottom, left to right sequence for scanning the ladder diagram. Now let me go to some of the rules, the basic rules which you should know when you are converting a logic gate into a ladder diagram. Here, when I have an input, I have an AND gate. In that case, the inputs of AND gate are represented as the contact in series. So if an AND gate has two inputs, the two contacts are to be shown in series. And if an AND gate has four inputs, the four contacts are to be shown in series. Then OR gate, for an OR gate, if it is a two gate, if it has a two inputs, those inputs are shown as contacts in parallel. And if OR gate has four inputs, all the four are represented as four contacts in parallel. And Whenever input is bubbled, input of a gate is bubbled, in that case, that should be shown as a NC contact, normally closed contact. Now, let us see an example how we convert all the four logic gates to a ladder diagram. The first one I have taken is AND gate. Here you could see I have a two input AND gate here. IN1 and IN2 are the inputs. Out 10 is the output. So the equivalent ladder diagram for two input AND gate is shown in this diagram. Here you can see, since this AND gate has two inputs, I have taken two contacts IN1 and IN2, and it's an AND operation. So it is A, AND operation is A dot B. So or it should be read as A and B. So this IN1 and IN2 contacts, they are connected in series, and then output 10 is also connected in the same rung here. So from the truth table, if you remember the truth table of an AND gate, when both the inputs are 1, the output is 1. Otherwise, it is 0. So you could, this is that truth table is that fourth combination in the truth table is evident in this ladder diagram. That is, whenever the contacts IN1 and IN2 both are energized, both will close. Thereby, it will complete a thereby it will establish a connection between two rails, and the output coil is energized. So as I said, an AND gate represents two switches connected in series with a bulb. So same thing here, there are two contacts connected in series. And the second diagram, it shows it's I have taken a four input AND gate. Here there are four inputs IN 1, 2, 3 and 4, and all these four are connected in series here. And then out to 2 is 12 is the output. So here 12 represents the output coil. This means that when all the four contacts are energized at a time, so all will close, and this will establish a connection between the two rails. Now OR gate, here I have taken a three input OR gate. The inputs are IN1, 2, 3, and the output is out 17. So OR gate, for an OR gate, the equation is, logic equation is the output y equal to a plus b. So when I have OR gate, all the inputs of OR gate, they are represented as the contacts in parallel. So three inputs I have taken. So in the ladder diagram, I have taken three contacts. Here you can see IN1, 2 and 3. These are the three contacts which represent three inputs of OR gate. And all the contacts are connected in parallel, and then the coil, output coil 17 is connected. Now looking into the working of this OR gate, in the previous session I said that an OR gate output will be 1 under two conditions: when both the inputs are 1, first condition; the second condition, when any of the inputs is 1. Hence, your OR gate, it can be represented as the switches which are in parallel. So here also I have connected the three inputs in parallel. Now the truth table will see how it matches, this ladder diagram matches the truth table of an OR gate. Here I'll assume that all the three contacts are energized, hence they'll close. And this provides a connection between the two rails. The output coil will be energized. That is first, the fourth combination in the truth table. Now I'll take a case wherein I'll energize 1 and 2. 3 is not energized. In that case, contact 1 and 2 will be closed, whereas contact 3 is open. Hence, there is a connection between the two rails and the coil is energized. Now I will take a case wherein only one contact is energized. Let me take ion 3 is energized. So it closes. Whereas the ion 2 and ion 1 will be open. So in that case, a connection is established between the two rails through ion 3 and the output coil is energized. Now let me take a case wherein all the three contacts are not energized. In that case, there is no connection between the rails, so the coil is not energized. Now let me move on to a NOT gate here. So here I've shown a symbol of a NOT gate, and in the last session I said that the NOT gate output is given as y equal to a complement. Uh, and here I have written a ladder diagram for a NOT gate. This here you could see IN22 is the input of NOT gate, out 63 is the output. So in the ladder diagram, I have taken a contact IN22 taken as NO contact, and then I have the output coil 62, and this represents an intermediate output, not the final one. Okay, and in the second rung, I have taken a contact CR62, and then it is taken as normally closed contact, and this produces an output 63. So the coil 63 gives the actual output y of the NOT gate, whereas coil 62 gives some intermediate output. Now we will see how the inversion will take place. I'll assume a case wherein the input is 1. The contact IN22 is energized, so this closes. Hence, coil 62 is energized. When 62 is energized, I have a contact by name CR62, and it is taken as NC contact. So whenever the output of the coil 62 is energized, this will energize the contact 62. When this is energized, the contact will open. Thereby, you are not energizing the coil 63, and hence here the output is 0. So I apply or I energize IN22, whereas the final output 63 is 0. So there is a inversion of the input at the output terminal of a NOT gate. Now I'll take a case wherein IN22 the input is 0. That means I'm not energizing the contact, so it remains to be open. When this is open, there is no connection between the two rails, hence coil 62 is not energized. When 62 is not energized, coil is not energized, you have a contact CR62 that is also not energized. When not energized, this contact remains closed, thereby energizing the coil 63. Therefore, there is a connection between the two power rails in the second rung of the ladder. So the output will be 1. So for 0 input, I am getting the output as 1, which is a complement of the input. So this ladder diagram now works as a NOT gate. Now we'll go through a XOR gate. A symbol is shown here, and the logic equation for XOR gate is y equal to A XOR B. XOR is the operation being done, and XOR is represented as a plus, and then it is encircled by a circle. Encircled plus represents a XOR operation. And when I expand this logic equation, I'll get y equal to A B bar plus B bar A. So for keeping that equation in mind, we can write a ladder diagram for XOR gate. I'll repeat, the output of XOR is given by Y equal to A bar B plus A B bar. So in that equation, we have two terms. One is A B bar plus A bar B. So here plus represents an OR operation. OR means the contact inputs have to be connected in parallel. Then we have A dot B bar. That is AND operation. So the inputs A and B bar of an AND gate, they have to be connected in series. So same equation I've used here. So you can see here, this represents A bar and this is B. They are connected, two contacts or two inputs are in series. So this represents the term A bar dot B. The second term is, it is represented as A B bar, A dot B bar. So these two contacts are in series because they are the inputs for an AND gate. And these two terms, in between these two terms, you have a plus sign indicating it's an OR operation. So the input for OR gate, that is one is A bar B and the second input for OR gate is AB bar, and they are connected in parallel. And this combination is connected to a output coil. Similarly, we can have ladder diagram for XNOR gate also. XNOR symbol is shown here and the logic equation is Y equal to A XNOR B, and XNOR operation is represented as a dot and then circle encircled around it. So a encircled dot indicates XNOR operation between the two inputs. And if I expand that equation, the output equation turns out to be Y equal to A bar dot B bar plus A dot B. So here also we have A dot B is there. So dot means OR operation. So to do the A dot B is there, that represents a AND operation. So AND operation means it has two inputs. Those two inputs are to be connected in series. And similarly, we have one more AND operation done between the variables A bar and B bar. So that AND operation is also represented as two contacts in series. And these two terms are OR together. So in between two terms, we have a plus. Plus indicates it's an OR operation. So they are OR together. So whenever I am ORing, the inputs of OR operation are to be connected in parallel. Therefore, this is the first term which represents A bar dot B bar and the second term A dot B. So these two are the inputs of a OR gate. Hence these two inputs, these two terms, they are connected in parallel. The next gate we'll study is about the not NAND gate. So I've shown a symbol of a NAND gate here. Here I've taken four inputs, IN1, 2, 3, 4, and the output is 27. So this NOT gate, as I said in the last session, it contains of two gates. It consists of two gates, AND gate and followed by a NOT gate. The same logic is used to write a ladder diagram for NAND gate. So here you can see this AND gate. There are four inputs here. So the inputs of NAND gate are represented as contacts. Four inputs are represented as four contacts in series. So you can see here IN1, 2, 3 and 4. These are the four inputs of AND gate and they are connected in series. and here 21 is the output here, and it is an intermediate output. It is not the final output y. Okay, then this output 21, this will energize the contact CR21, and this is taken as a NC contact, normally closed contact, and this contact energizes a coil 27. So 27 represents the actual output of NAND gate. Now we have a NOR gate. NOR gate is the symbol is shown here. I have taken three inputs for this NOR gate. And again, this NOR gate is combination of two gates. It is OR gate followed by a NOT gate, and three inputs are shown here. So because it's a OR operation is done between the three inputs, hence these three contacts are represented as three contacts in parallel. So this is shown in a ladder diagram. All the three contacts, they are connected in parallel. Then it is the output of OR gate is inverted using a NOT gate. Hence, whatever the output 112 coil you get, that energizes another contact CR112, and this is taken as a NC contact. That is, whenever the contact output 112 is energized, the contact CR112 will be energized and it will open. So I think this finishes your current session. So in this session, we went through what ladder diagram is, what are the fundamental paths used to write a ladder diagram, went through some of the rules, general rules used to used for conversion. Then we took seven basic gates and converted into a ladder diagram. So next we'll quickly move on to the quiz section here. Okay, the question one is which gate has its output on when the inputs are same? When inputs are same, suppose if it has got a two input and the two inputs are they have the same value, then which gate has its output on? The answer is XNOR gate. Here, in an XNOR gate, whenever the inputs have the same value, the output will be 1. The second question is which gate has its output on when all the inputs are on? The choices are OR, NOT, and NAND. The answer is AND gate. So for an AND gate, the output becomes on only when all the inputs are on. Otherwise, the output of AND gate is 0. The third question is which gate has its output on when any one of its input are on? The choices are AND, OR, NAND, XOR. The answer is OR gate, choice B. For an OR gate, uh, when all the inputs are 0, the output is 0. When all the inputs are on, the output is on. and when any of the input is on, then the output of OR is 1. So the answer is OR gate. Question 4. NAND is combination of dash and dash gates. Choices: A, OR not, B, and not, C, and, D, or NOR. NAND is a combination of and not. So the choice is B. NAND is combination of and not gates. So first will be the AND gate and followed by NOT gate. That entire combination gives us NAND gate. The fifth question is NOR is combination of dash and dash gates. Choices are AND, NAND, B, or not, C, and not, D, or XOR. NOR is combination of OR and NOT gate. So the answer is B. Choice B. So first will be the OR gate followed by the NOT gate. This combination of two gates will give you the NOR gate. The sixth question is two input AND gate is represented in ladder diagram as choices are two contacts in parallel, B, seal contact, C, two contacts in series, D, none of the above. Two input AND gate is represented in ladder diagram as two contacts in series. So the answer is choice C. So this is will end our present session. So in the next session, we'll be covering some more logic circuits, and which is a combination of AND, OR, NAND, NOT gates. And given that logic circuit, how you can convert it into a ladder diagram. That is one part of conversions, and I'll will be giving you the ladder diagram and how can you convert back into the logic circuit. So these two types of conversions between logic circuit and ladder diagram will take it up in next session, and thank you.